Hello everybody and welcome back to my SP2 channel. So this video is all about the nature of light. We have introduction, light as a wave. We're going to be looking at the electromagnetic spectrum, a little bit about the common units that we have for wavelength, light as a particle, and I also have a practice for you. So this is the first lesson of my favorite chapter, which is the electronic structure of atoms. It has a lot of physics concept for sure, and honestly, I love physics more than chemistry, so I'm not sure how I ended up being a chemist, but let's dive in and explore the fascinating world of atomic structure. Okay, so starting by this really good question, like what is light, right? So think about light as a form of electromagnetic radiation that can exhibit both wave and particle-like behavior. Okay, so think about it as like wave-particle duality, which is pretty cool. The light that we can see with our eyes is just one type of the electromagnetic radiation, which is known as a visible light. Okay, I'll show you a picture in just a moment. But all of these lights are going to have the wave-like characteristics similar to what we have for like water wave. Okay, so let's say that you drop a stone, or we have a boat moving in water, and that's how we can create waves, right? So I'm going to show you a picture of wave on the next slide, and we can look at all the important features of waves. Okay, so let's look at the light as a wave. The fundamental properties of wave, just like what we have for water wave, can be applied to all of the waves that we have, including the light waves. Okay, so take a look at the right side. You've got water wave, and I have the first key concept, which is periodicity, and that is the wave that following a repeating patterns of peaks and troughs at regular interval, right? That's how we call that, a period. Then we have the wavelength. We are using lambda. This is a Greek letter, presenting the distance between two consecutive peaks or two consecutive troughs in the wave. Okay. I have another important concept, which is frequency, which is presenting the number of complete wavelengths, right, that pass at any specific point, but it has to be per second. Okay, we're going to be dealing with these two, the wavelength and frequency, a lot when we are doing our study in the electronic structure of the atoms. Okay, cool. Now here is my electromagnetic spectrum. Okay, so you can think about the range of all the possible electromagnetic radiation, and we can categorize them by wavelength or frequency. Okay, so take a look at the right side. That's where we get the picture, and I'm just going to read all of these for you. So I've got my gamma rays, I've got the X-ray, we have the ultraviolet, which is right above the violet, right? And then I have all the colors, the 7 colors in our visible light. We have infrared, below red, microwaves, and then I also have radio frequency, right? And as you can see, the wavelength is at the top. We have the shortest wavelengths here. And then I have the highest frequency, right, for my gamma rays. So let's look at why these two are inversely proportional. So all of these lights that we have, all different types of lights, they are going to travel with exact same speed, which is known as the speed of light, in vacuum. Okay, and that will be about 3 by 10 to 8 meter per second. So if the speed is going to be staying the same, then the frequency and the wavelength must be inversely proportional. And I want to ask you guys to always remember this relationship. You take your wavelength, you multiply that by your frequency, and that is going to give us the speed of light. This is a very important relationship for our discussion. Okay, cool. Okay, so this table is presenting all the common wavelengths units, and honestly, depending on the light that we're dealing, there are some units that are more convenient. Like for example, if I am working with X-ray, then I prefer to say angstrom, right? Which is going to be 10 to negative 10 meter. But if I'm dealing with, let's say, microwave, then it's probably easier to go by either millimeter or like centimeters, right? You don't need to really memorize these. Just be aware that depending on the light and the experiment that we're doing, right, there are going to be some of these units that are more convenient than the others. Okay, cool. Okay, so we already have talked about the wave behavior. Now we're going to be focusing on the particle behavior of the light. Okay, so there has been many experimental observations, such as photoelectric effect, that is actually showing us that the light can also behave as a stream of particles, which is known as photons. So everybody listen up. I'm going to explain this experiment here for you. Okay, so what I have here is just a piece of metal, and we are shining a specific light on the surface of this metal. Okay, so listen up. Under the right conditions, photons striking a metal surface can transfer their energy to electrons in the metal. A certain amount of energy, which is what they call work function, is required for the electrons to overcome the attractive forces holding them in the metal. Okay, now if the photon striking the metal have less energy than the work function, the electrons do not acquire sufficient energy to escape from the metal. Okay, now what's interesting here is increasing the intensity of the light source does not lead to emission of the electrons from the metal. Only changing the frequency of the incoming light has that effect. Okay, and in fact, Einstein won the Nobel Prize in Physics in 1921 primarily for his explanation of this photoelectric effect. So that is pretty cool, right? So that's why we need to have like quantized energy, right? And we can calculate the energy of this quantized energy, or let's say discrete energy, using the Planck's equation, which is given here. So my E here is my energy, H is just the Planck's constant, right? And this would be the frequency. That's another important relationship that we need to remember for our discussion. Okay. Now, let me do a quick comparison for you. Anytime that we say we have continuous energy, you can think about we are taking a ramp and going up. So our energy here is going up gradually, right? But if you have a quantized energy, then it's going to be very specific steps. It seems that you're taking one step at a time, or maybe you can jump from here to here, but you're not going to be able to stay between the two steps, right? That's how we can think about quantized energy. Okay, excellent. So let's do this practice together. The question is, calculate the energy of one photon of light, and this is the specific light, which is yellow, and the wavelength is given as 589 nanometer. Okay, so the first step is we have to calculate our frequency. Using our relationship, which is C over our wavelength, we can calculate our frequency. Be careful with your units, right? It has to be meter. So I need to convert my nanometer to my meter, which is 10 to negative 9. And then you can plug it into your energy equation to calculate your energy. Okay, excellent. So this video is scheduled to be published on Valentine's Day. Happy Valentine to all of you around the world. I hope every day feels like Valentine's Day, filled with love, joy, and happiness. God bless you. Take care and see you soon on the next video.